Okay, so the next one that we're going to talk about in today's lesson is going to be a shared pointer. And this is going to allow us to have, say, multiple shared pointers pointing to some sort of dynamically allocated object. And I don't know, I like the integer value of 7, so let's go with that. So let me write out how this is going to get set up. Whoops, same object. And then after I get this set up, I'll talk about a little bit of the implementation so that you can better understand what's more or less happening behind the scenes. Okay, to kind of, I guess, run through the motions here. The idea is that once no shared pointers are pointing to this object anymore, so when the final shared pointer that was pointing to this here is destructed, we want the dynamically allocated object to also be destructed. So we're hanging around till the last shared pointer to the object standing. Once it's teared down, we'll go ahead and deallocate the memory associated with the dynamically allocated object pointed to it. Think about how this is different from the unique pointer. Unique pointer, we were dealing with a single object that was essentially storing a raw pointer to the integer object on the free store, storing 7. And then we acquired that resource in the constructor. We deallocated that resource, so the dynamically allocated integer, upon the tear down of pointer. So when pointer was being destructed, its destructor was defined in a manner that would free or release the dynamically allocated integer, in this case, that it was pointing to. Here, the process is going to be a little bit different. So you can see in our declaration here that pointer is being initialized with a new free store object. So this new integer object in the free store is going to have its memory allocated. It's initialized with 7. And then we're using that object to initialize our first shared pointer, PTR. Okay, so let's think about this construction real quick. At this point, there is one pointer to this object. Now notice here, we have another shared pointer being created, and it is initialized with an object as the same type. So for this type, copy semantics are defined. The reason being is we have to set up the shared relationships. And once we hit this statement right here, we can see that we have a second pointer to that object. And notice here, PTR and PTR2 are sharing the dynamically allocated integer object, storing the value of 7. And how this was set up was that on the copy constructor, a couple things happen. First, there was somehow a relationship was made, right? Okay, so if we think about how shared pointer might be defined at this point, let me draw this out real quick. It's definitely going to store a pointer to the shared resource, right? So, I mean, think about this as a raw, or as a shallow copy. In the case that at the end of this statement, we have two objects, both of which have a pointer to the type T, storing the address of the same object. So in this case, the address of that dynamically allocated int residing on the free store. So let me draw this out even more a little bit. Actually, let me update the drawing entirely. Okay, so back to our kind of friendly memory diagrams. So again, at this point, we have two shared pointers sharing a dynamically allocated object. They're both pointing to it, right? And there's instances in our program where this might be beneficial to set up, and that multiple objects can share some sort of resource, or that we might want multiple pointers to some shared resource, which is what this is providing. Now, remember the case with the raw pointers. We could set up multiple pointers to the same object, but there was no way to kind of determine whether or not the resource was free, when the resource should be freed, etc. There was all this additional counting that we'd have to do. Now, in this case, we said that, okay, somehow the shared pointer is going to manage and determine that when the last shared pointer standing is pointing to the dynamically allocated resource, we'll go ahead and once its lifetime is up, free that resource, which means that shared pointer is not only going to have one pointer in the definition as a data member, it will have two. The second pointer is going to be pointing to what's known as a control block. So I'll just write control, and this will be shared between the two shared pointers. And this will also reside on the free store. Now this shared block, and I'm going to write this out, I'm not going to necessarily put in too much information, but it will contain a reference count, which is how many, so let me write this out, reference count. How many shared pointers are pointing to this object? So think about this. When we hit the copy constructor or copy assignment operator, we would increment the reference count by 1. If any of these shared pointers' lifetime is over, we would decrement the reference count by 1. When the reference count is precisely 1, that means that we have the last shared pointer standing. So the destructor for the shared pointer is going to access the control block, which has some additional information and is not just limited to what's being drawn here, but it will go ahead and check that account. If the count is 1, it would know that, okay, after this shared pointer is destructed, there's no other shared pointers pointing to this resource. So I need to go ahead and call delete on the resource pointer. So on the address stored here. And then, additionally, since the control block is on the free store, well, we'd go ahead and deallocate memory with that too to clean up. But notice how easy this makes kind of the copy semantics to work. If we wanted to create a new shared pointer, or excuse me, not create, but a new shared pointer to this integer object that we have. So if we did something like auto ptr3 equals pointer, that's just going to be a shallow copy of these two data members. I mean, pointer, I guess I don't really have room to draw this, but here, let's move this down and go through the motions together. So that's going to be a copy constructor, right? Because we're initializing pointer 3 with an object of the same type. So let's go ahead and just write ptr3. It's going to have two data members, a pointer to the resource and a pointer to the control block. We'll go ahead and put a little box around this. I'll go ahead and pull up our memory diagram a little bit. But I mean, this is just a shallow copy, right? So whatever was in PT1, PTR's resource field would be defined to be shallow copied into PTR's 3. So at this point, they're both pointing to the same object. We just created that shared kind of relationship here. Next thing we do is go ahead and hook up the shared control block. And then the third thing we do is increment the reference count by 1 to 3. And we continue this process, right? And because the control block and the object reside on the free store, they're not associated with, they're not controlled by the stack. So if PTR3's memory is deallocated, notice in that case, the dynamically allocated objects are sticking around, right? Because they're not controlled by the stack. They're controlled by the free store manager. And then they're on the free store. So we'd have to ask the free store manager to deallocate the memory. So at that point, notice that this is still hanging around. So if we went ahead and deallocate PTR3 and remove it from the stack, we just have to make sure that the destructor is decrementing that count by 1. And then if we, were to go ahead and deallocate, let me use some red here. So this one's been deallocated. Let's say we deallocate pointer 2. Well, in the destruction process, yeah, those links get kind of cut here. And of course, because we're deallocating a shared pointer, Our reference count goes down by 1. Okay, now let's say we go ahead and the lifetime for PTR is up. So this one's going out of scope. Well, in that case, the reference count, oops, let me go back. So pointer 2 went out of scope. So now the resource count here is going to be 1. Now let's say that PTR's lifetime is up. At this point in the destructor, it notices, hey, the reference count is 1. So I need to deallocate memory associated with the control block, as well as deallocate the memory associated with the dynamically allocated object that was once stored. So isn't that like, it's kind of neat, right? So the memory for the dynamically allocated object is being managed by our shared pointer objects. And they know kind of about one another. I mean, you can't access one through the other, but they're all pointing to the same control block, which is containing some housekeeping information to allow it to determine, well, if PTR3 goes out of scope, well, there's still 2 things pointing to that resource, so it's still in use. If PTR2 goes out of scope, okay, there's still another thing pointing to that object, which means it's still in use. When the final one goes out of scope, well, nothing's going to own it after that. So we go ahead and we go through the motions, deallocate the resource, free it up, and there's no memory leaks happening here. They're avoided, and we're not having to kind of worry about, well, in this function, we have a raw pointer to this object. In the other function, they're kind of all scattered throughout our program. Pointers are being passed from place to place. Here, we understand that ownership isn't exclusive, but we also know when the resource is no longer needed and can easily or automatically, this type will perform the deallocation for us.